So this is problem 4 from practice exam 2 for exam 2. So this is a multiple choice question asking, suppose we randomly throw n uniquely colored balls into n different sized baskets, where each ball has a equal probability of landing in each basket. And so this problem is asking us to find the probability that each basket contains exactly one ball. So this is a counting problem. And first with counting problems, it's always important to identify what it is that we're counting. So this problem is talking about the n uniquely colored balls. And it's important to note that because each of the each of the balls have a unique color, all of the balls can be distinguished from all of the other balls. So we can say that the balls are distinguishable. This problem is also talking about baskets. And it's saying that the baskets are all differently sized. So each basket can also be distinguished from all of the other baskets. So each basket is unique as well. So we can say that the baskets are also distinguishable. And so this is important, the fact that the balls and baskets are all distinguishable, that they're all unique, because it means that every possible scenario is of like a basket in a certain ball or so ball in a certain basket is a unique scenario from all the other ones. So we're not going to be over counting like many different scenarios. So this actually would simplify the problem. So the next thing the problem is asking us to actually find the probability that each basket contains exactly one ball. So probability can usually be thought of as a ratio or a fraction, where the denominator will be the number of all possible total outcomes. So in this case, it would be like all of the different arrangements of balls and baskets. And the numerator can be thought of as all of the outcomes that we care about. So this problem, the type of outcomes that we actually care about are the ones where every basket contains exactly one ball. So I think usually it's easier to start by finding the denominator, counting the number of total outcomes there are. So just, okay. So the way we can think of this is by counting based off of the balls and then counting by the baskets. So if we have each of our n balls, so let's just pretend these spaces are balls, and they go up to, like, let's say n. If we were to look at each of these n balls individually, we can say that ball 1 has n baskets it can go into. So it has n options for the basket which it can go into. Ball 2 also has n options for the basket it can go into. Ball 3 also has n options, etc. So all of the n balls have n options for which basket we can place that individual ball into. And because this would be happening, we can think of this happening as a sequence. So first we would be like assigning ball 1 to a basket, then ball 2 to a basket, then ball 3 to a basket. We can think of this as multiplying the number of options for each ball. So we can think of this as multiplying the number n, which represents the number of baskets there are, n times, which represents the number of balls. So n times n, or sorry, n multiplied together n times would give us n to the power of n. So this is going to be our denominator. This is all of the possible like outcomes for arrangements of balls and baskets. So now let's find the numerator, and I'll just erase some of this stuff. So the numerator is going to be, again, we're going to be counting the number of outcomes that we actually care about. So before, for the denominator, we were counting based off of like the balls first. So we were going through each of the n balls and seeing what are all the options for the baskets in which we can place each of the balls in. Now for the baskets, or now for the numerator, we can actually count by the baskets, because the thing that's defining this scenario is that each basket must have exactly one ball in it. And so the way we can think of this is, say we have basket 1. Basket 1. So this is the first basket. We have not assigned any balls to baskets yet. So since we have not assigned any balls yet, we can put like the number of options of balls for which we can put into basket 1 is n. We can put any one of the n balls into basket 1. And then Once we do that, we would next be choosing which ball to place in basket 2. So because we already have removed one ball from our collection of balls and put it in basket 1, we now don't have n options anymore for the number of balls we can put in basket 2. The number of options for balls we can place in basket 2 is actually n minus 1 now, because we now have one fewer ball compared to the number of options we're putting into basket 1. And then running out of space, but we can go here. For basket 3, then we would have n minus 2 options. Basket 4, n minus 3, etc. So if you notice this, because this assignment is also happening in a sequence, we can think of it as like, okay, let me do some more erasing. Let me erase this. We can, since these assignments of the balls and baskets is happening in a sequence, we can also multiply these numbers together. And this will happen n times, or yeah. And if we notice this sequence right here, we can see that this is actually the factorial function. This is what n factorial would be. As in, we're starting with n, then multiplying by the number 1 less than n, then by the number 1 minus n, or 2 minus, sorry. We're going to start with n, multiply by the number that's n minus 1, then multiply by the number that's n minus 2, all the way down. So this is going to be the number of outcomes we care about. And in this problem, the outcome we care about is an outcome where every single basket has exactly one ball. And we know for a fact that this number counts all those scenarios because the way that we assigned it is that each basket has only one ball. This is not the number of balls in the basket. This is the number of options from which we can pick that one ball from. But the way that we've done this counting, we've basically essentially like forced only one ball into a basket. So we can write n factorial up here, and then we can look at our answer choices, and it looks like answer choice E perfectly matches what we found. So the answer to this problem is E n factorial over n to the power of n.